Here is something that should make you uncomfortable. A kilometer-wide rock has been crossing Earth's orbital path approximately every 10 months for as long as humans have existed. Astronomers discovered it in 1997 and have been tracking it for 29 years. In that time, it has made roughly 40 close approaches to our planet, and as of right now, we don't know how big it actually is. On Friday, for the first time in those 29 years, NASA is pointing radar at it, and we have about 48 hours to learn something we probably should have known a long time ago. What they find, and what we've been doing instead, reveals something about our planetary defense system that nobody in the mainstream space media is talking about. This is not a safe fly-by and move on story. This is a question about what we know, what we've lost, and whether we'd actually see the dangerous one coming. Asteroid 1997 NC1 passes Earth on Friday at 11:16 in the morning Universal Time. It will come within about 2.56 million kilometers, roughly 6.5 times the distance to the moon. By astronomical standards, that's a close encounter. By planetary defense standards, it's a rare opportunity. The asteroid belongs to a class called Atene type, rocks whose orbits are largely contained within Earth's own orbital path around the Sun. 1997 NC1 spends most of its time closer to the Sun than we do, then swings outward, crossing Earth's lane every orbit. It's been doing this for millennia. We just didn't know it was there until 1997, when NASA's Near-Earth Asteroid Tracking Program caught it during one of its crossings. Since discovery, astronomers have calculated its orbit with high confidence. It is not going to hit Earth, not Friday, not at any point in the next 107 years at minimum. That part of the story is settled science. What isn't settled is what this rock actually looks like. Current size estimates range from 710 meters to 1,600 meters. That's not a small margin of error. That's a factor of 2. A 710-meter asteroid and a 1,600-meter asteroid are not the same threat in any meaningful way. A 710-meter impactor would be capable of devastating a region, destroying a metropolitan area and everything around it for hundreds of miles. A 1,600-meter impactor, operating at the right angle and composition, is something closer to a civilization-altering event, the kind of impact that drives long-term climate effects and global disruption. The reason that uncertainty exists comes down to a problem called albedo. From a distance, telescopes can measure how much light an asteroid reflects, but a large dark asteroid and a small bright asteroid can produce identical light signals. Without knowing the surface reflectivity precisely, size estimates remain wide, and the way to resolve that uncertainty, to actually measure the shape, rotation, and structure of an asteroid with precision, is radar. Specifically, it was Arecibo. The Arecibo Observatory in Puerto Rico operated for 57 years as the largest single-dish radio telescope on the planet, 305 meters in diameter, built into a natural sinkhole in the mountains. Among its many functions, Arecibo was the gold standard for near-Earth asteroid characterization. It could send a radar pulse toward an object like 1997 NC1 and reconstruct its three-dimensional shape from the return signal. It could measure rotation rate, surface roughness, whether an object was a solid boulder or a loosely bound pile of rubble. That distinction matters enormously for any future deflection scenario. You cannot push a rubble pile the same way you push a solid rock. On December 1st, 2020, a structural failure caused Arecibo's instrument platform to collapse onto the dish. The telescope was destroyed. It has not been rebuilt. Since then, the primary radar tool available for near-Earth asteroid characterization in the United States has been the Goldstone Solar System radar in California, a 34-meter dish. That is not nothing, but it is not Arecibo. The resolution is lower. The sensitivity is lower. The kinds of detailed internal structure data that Arecibo produced are not achievable at the same quality. For the 1997 NC1 flyby this Friday, NASA is using Goldstone, specifically a 34-meter transmitter and a 34-meter receiver, to obtain the first radar observations of this object in its documented history. For 29 years, this rock has been listed in the planetary defense catalogs as potentially hazardous, with a size estimate that varies by a factor of 2 because nobody had the opportunity or the resources to point radar at it during a previous pass. Friday is the first real chance. What they find will be genuinely new information. In all likelihood, it will narrow the size uncertainty significantly. It may reveal rotation characteristics, approximate shape, and surface texture. It will make 1997 NC1 a better understood object. But here's the part worth sitting with. This is not an emergency scenario. This is a planned scientific observation made possible because the asteroid happens to be close enough right now. If the situation were different, if orbital calculations showed a higher probability of a future close approach with meaningful impact risk, we would want this kind of data immediately and at the highest possible resolution. And the highest possible resolution tool we had was destroyed 6 years ago and has not been replaced. Planetary defense is not just about detecting asteroids. Detection is step 1. Step 2 is characterization, understanding what you're dealing with well enough to plan a response. Step 3 is, if necessary, deflection. We demonstrated a version of Step 3 in 2022 when NASA's Goddard spacecraft successfully altered the orbit of the asteroid Dimorphos by impacting it at high speed. That was a genuine achievement in planetary defense. What 1997 NC1 illustrates is a persistent gap in Step 2. We have a catalog of roughly 2,300 potentially hazardous asteroids. Most of them have well-determined orbits. Fewer of them have detailed physical characterizations. The ones we know the least about structurally are the ones we would struggle most to deflect effectively, because deflection strategy depends on composition. The asteroid passing Friday has been in our catalog for 29 years. It is making its closest approach since the year 1600. It will not return to this distance until 2133, and we are getting our first detailed radar look at it this week with instrumentation that is less capable than what we had 6 years ago. That is not a catastrophic failure. It is not an emergency, but it is a clear signal about where priorities have been placed. Arecibo's successor has been discussed for years. Nothing comparable has been built. The James Webb Space Telescope, which cost $10 billion, looks outward at distant galaxies, the early universe, exoplanet atmospheres. The telescope that looked inward at the things in our immediate neighborhood, the ones that actually cross our path, is a pile of wreckage in a Puerto Rican sinkhole. Friday's flyby is not a close call. It is not a threat, but it is a demonstration. A kilometer-wide rock tracked for 3 decades, making its closest pass in over 4 centuries. And we're seeing it clearly for the first time this week. If you were building a planetary defense system from scratch, that's not how you design it. So here is the question I want to leave you with. We've now had 2 confirmed examples of asteroids we didn't see coming until very late, Chelyabinsk in 2013 and the 2019 object that passed inside the moon's orbit and was detected only a day before closest approach. We've had a near miss in 2012 that nobody noticed until years later. And now we have a known, tracked, cataloged object with a size estimate that spans a factor of 2. What would it take for you to feel confident that we'd see the dangerous one coming? And how would you know whether we have that capability or not? That's not a rhetorical question. I genuinely want to know what you think.